Hey, I'm Connor. This is Shadaj. We're PhD students at UC Berkeley, and we're going to be telling you about our vision for how database researchers can help the correctness of queries for the popular CRDT programming framework. This work is part of the Hydro project at Berkeley, where we're building a optimizer and declarative interface for distributed systems, and it wouldn't be possible without all of these amazing people. So why are we talking about CRDTs at a database conference? Well, CRDTs have gotten very popular, certainly amongst academics writing lots of papers about them, but also amongst developers talking about them on Hacker News and in blogs. And recently, they're getting commercialized in startups more and more for things like collaborative editing, building applications that are often offline, like for airplanes, or building responsive web applications. So what are CRDTs? I'll give a quick overview. You can find more details in the paper or on our TikTok. But CRDTs stand for conflict-free replicated data types, and they're an object-oriented interface to a replicated state that is going to give eventual consistency. So in particular, you define three operations on your replicas: an update operation that modifies the state of a replica, a merge operation for combining the state of two replicas, and then a query operation for reading the state of the replicas. And they guarantee strong eventual consistency of state as long as you meet certain properties on the update and merge functions that in summary mean that the state grows monotonically over time. So this is great. We have a way to have strong eventual consistency of writes and of reads. What more could we ask for? Well, not so fast. CRDTs guarantee strong eventual consistency of writes, but they do not make the same guarantee for reads. This introduces a foot gun, where people building applications out of these might be under the impression that they're getting a strong eventual consistency guarantee for their queries, when in fact it's only true of the state. And as database folks, you're probably wondering, what good is state if you can't query it? Well, how have these CRDTs gotten so popular if they're not giving strong guarantees on queries? One reason is that a lot of the applications where they're being used are human-facing. For example, collaborative editing. You're editing an overleaf with someone leading up to a paper deadline. And inconsistencies in this setting, you can kind of deal with via the common sense human aspect of interaction. If I'm not seeing some updates to a section in the overleaf, but I'm pretty sure that you edited the section, I can just message you on Slack and say, what's up? And resolve like delays and stuff like that this way. And CRDTs are also used in backend applications without kind of humans in the loop, which is the applications that we're focused on in this vision, how to make these applications have strong guarantees on queries. So let's take a look at the Amazon shopping cart example from the Dynamo paper. So here we have shopping carts where we represent the state as a set of items that have been inserted and then a set of items that have been removed from the shopping cart. And this makes the state grow monotonically and allow it to be represented as a CRDT. So say we are thinking about having baked potatoes for dinner. We order a baked potato, and we also are window shopping Ferraris on Amazon and accidentally add a Ferrari to our cart. And this gets replicated to the other replicas in the system. But it's no big deal. We just remove the Ferrari from our shopping cart. But this operation is slow to get replicated. And some queries we might ask in this setting are perfectly fine. For example, we want to automatically check shopping carts for luxury items and send promotional emails to users who might be likely to buy luxury items. On the other hand, some queries, like the checkout query, are going to have an issue with this delay. When we go to checkout in a coordination-free way where we only read from one replica, the query is subtract the removed items from the inserted items. Of course, we have not learned about the removal of the Ferrari. As a result, we are going to be spending a lot of time on the phone with Amazon customer service trying to get this undone. We call this Schrodinger's consistency. CRDTs guarantee consistent updates, but queries are unsafe. So are CRDTs useful if we can't query the data? Well, they are, and we can see how we can use them safely by distinguishing between queries that are safe to do coordination-free versus queries where they're unsafe to do coordination-free, but will be correct as long as we do a coordinated read. And in our example, our luxury items query is coordination-free. Our checkout query is not, because of the presence of monotonicity in the first query and not in the second. And this is something that we know about from the Calm theorem from database theory that tells us that the queries that can be calculated coordination-free and consistently are exactly the queries that are monotone. What does monotonicity mean? Well, in relational algebra, 4 of the 5 base relational operators are monotone. Select, project, union, and join are all monotone operators. And monotonicity is compositional. So any query that's made up of those base operators will be monotone and therefore can be computed coordination-free. On the other hand, set difference is non-monotone, and queries using set difference will require coordination in order to be consistent. And that's what's happening in this checkout query for the shopping cart, because set difference is the operator in the query. Now, Shadaj is going to tell you about the implications of this distinction between monotone and non-monotone queries and what we have to offer as the database community.
Thanks, Connor. So yeah, we have this really nice distinction now between monotone and non-monotone queries, and that tells us when we need coordination to get consistent results from a CRDT. But in the traditional object-oriented view of CRDTs, where every client just has a local object which they can do whatever they want with to interact with the CRDT, this is hard to enforce because the developer might want to execute arbitrary logic, and we have no safeguards on that. To impose safeguards and make sure that developers don't have to be worrying about this monotonicity, non-monotonicity issue, and the system handles it for us, we get something that looks a lot more like a database, where instead of developers interacting directly with the CRDTs, they interact with the more general database, which is using CRDTs under the hood for eventual consistent replication. Now, the first step of building a database is defining a query language. And this is particularly important for CRDTs because we need to be able to analyze queries to determine what amount of coordination is required to safely execute them. As you saw before, if you have a monotone query that's involving things like counting with Boolean functions or a threshold, that's all safe. But the moment you try to do something like set difference, we need coordination and quorums in order to get a consistent result. Now, in addition to the query having to be monotonic, we actually have to be a bit more careful than that, because if we have our CRDT state, which is monotone to begin with, because that's one of the guarantees of a CRDT, and we have this monotone query on top of this, the composition is also monotone as a whole, and that's what makes things correct. But if we were to layer this with downstream behavior in our application that's non-monotone, then we would run into issues, because even though everything was monotone up to that downstream behavior, the fact that we do something non-monotone with it later completely invalidates the consistency guarantees that we thought we had. So how do we actually enforce that this end-to-end application is behaving correctly? We can do that by restricting the API surface to our CRDT database. So instead of offering the traditional uniform API for queries, we actually break this down into a couple cases for different guarantees. So the first one, the classic one, is a selection, where you have some monotone function, which is going to filter a set of elements to the ones we want. And we interact with the result of this in kind of an event-based manner, where as new rows appear, then we can execute some logic with them. And because we know this function is monotone, this is safe to execute on a single replica. Similarly, we can wait for some condition to be satisfied. So for example, we may be waiting until we've identified some luxury items in a user shopping cart, and then want to execute this logic to send a promotional email. If this function is monotone, which means that once it's satisfied, it won't be unsatisfied later, we're safe to execute this on a single replica, because we can just keep on checking this condition, and when it's satisfied, we can execute the downstream logic. The last two cases are a bit more complicated because they involve non-monotone functions. So the first situation, we can just execute a quorum. And a user has to explicitly opt into this because it does mean that the performance characteristics of this query will be affected. But in this case, they can execute a non-monotone function because we'll make sure to check with several replicas to get an accurate snapshot of the global state. And lastly, there are certain situations where a user knows that they can tolerate weaker levels of consistency, such as strictly weak or reader writes. And in these situations, we can allow non-monotone queries to be executed on a single replica, but with the caveat that the developer needs to be careful to make sure that their application will tolerate potential staleness in the results of these queries. But across these four cases, we now get this nice API surface where, as long as we can determine whether the function is monotone or not, the database can automatically decide how to execute this query, either on a single replica or on several. Now, one of the challenging parts is how do we actually determine if this function is monotone in the first place? And that's been an active area of research within our group on the Hydra project. We've been developing this data flow language called HydraFlow, which allows you to describe complex data flow pipelines. But the key trick and exciting component here is that we actually have a type system, which can determine whether or not components of your data flow are monotone or not. So for example, if we have a set which we know is monotonically growing and we're checking for membership of an element, the type system can actually determine that this overall query will be monotone. And so we're excited about using HydraFlow as the foundation for these CRDT databases to automatically determine the level of coordination required to execute a query. And you can check out more about HydraFlow on our website and check out the docs. And so with this, we actually have a nice picture here. CRDTs can be useful after all. We have coordination-free mutations as always because operations are designed on CRDTs so that they can be always executed on a single replica. But even for the queries, we can give stronger guarantees than the defaults that CRDTs have provided thus far. If you have a monotone query, they can be consistent on a single replica. And if it's not monotone, as long as you use a quorum, you also get consistent results. And this provides this nice uniform API service for developers to build applications on top of. Now, the last thing we'd like to touch upon is the internals of this database. So far, we've described the API surface, but now that we've actually packed these CRDTs behind the layer of a traditional database, we get some opportunities because we control how these CRDTs are replicated and placed on different servers. Specifically, we want to focus on three key aspects of database: extensibility, the ability to introduce new types into our system, handling these quorums, because these are a critical element of how performant our applications will be, and garbage collection to mitigate some of the challenges with memory utilization of CRDTs. First, extensibility. This is a critical element of a CRDT database because unlike traditional databases where most of your data sits in relations, CRDTs often have domain-specific merge functions where you have some specific knowledge about how to combine concurrent operations. And so developers will often find themselves designing custom CRDTs for different scenarios. Now, CRDTs have these strict mathematical properties that they need to satisfy in order for the replication logic to be correct. But we want to make sure that developers don't make mistakes in satisfying these properties. One of the exciting areas of research that our group has been focusing on is correct by construction CRDTs. So rather than relying on developers to satisfy these properties, we can actually provide primitives within the database that developers can build on top of to make sure that their custom CRDT designs will automatically satisfy the guarantees needed for safe replication. If you're curious to learn more, check out our papers on Anna, which is a key value store based on CRDT-like data types, and Katara, which is a recent work from our group on automatically synthesizing CRDTs. Next, quorums. As we discussed, CRDTs automatically do coordination-free mutations. So whenever you execute an operation, they'll execute on a single replica. And these are low latency. But the other half of this is that if you have a non-monotone query, it now needs to go to every replica in your system because you don't know where an operation may have been executed. And that means it incurs a very high latency penalty. Now, one of the great things about CRDTs is even though operations can be executed on a single replica, that doesn't stop us from executing them on several. And so we get this tuning opportunity where we can adjust the quorum ratios. And this is particularly exciting for CRDTs because regardless of how these quorums are tuned, you always preserve the happy path of monotone queries, which can be executed on any replica for consistent results. And so an exciting area of future research that we're looking to is dynamically adjusting these quorums based on when users are executing non-monotone queries, operations, and monotone queries, and taking all those into account. Lastly, memory utilization. This is a particularly challenging aspect of using CRDTs because since the state of a CRDT has to be monotone, oftentimes you accumulate a lot of information that's not actually going to be used in your queries. Because we have a database architecture for CRDTs, you get the opportunity to actually perform coordination in the background. Because we own all replicas, we can use coordination to identify data that'll never be revealed by a query and therefore can be garbage collected away. And we think this is a great opportunity to use CRDTs, gain the coordination-free benefits of them, but avoid the excessive memory utilization that often shows up. So in conclusion, we're really excited about CRDTs as a popular and developer-friendly tool for replicating state, providing a nice API surface. But the queries are not that great. They're unsafe by default. But thankfully, by applying monotonicity results from the Kahn theorem, we have a way to systematically ensure consistency in a way that a database can automatically analyze queries that are coming in to make sure that they're appropriately executed with the right level of coordination to get developers the safe results they need. So if you want to learn more, check out our paper. And we have lots of docs on our website about the related projects we discussed, like Hyderflow at hydra.run. And we're also on Twitter if you want to follow our work. Thanks.